Very good. Next, we're going to look at taking scalar valued functions as integrands. And the way that we establish that is the way that it's always done. We look at Riemann sums. So the only thing that's different is that we're now placing a function at a point. Note the notation. That means that we're looking at a scalar valued function, and we want to take that as integrand. So let's write this out. We have a double integral. We want to take as the domain of integration a surface. If we're going to integrate over that surface, we need to integrate with respect to changes in the surface area. But at any point and at all points of that domain, we want to evaluate a function. The domain is a surface. Assume that it's in 3 space, so any point on that surface will be given by an x, a y, and a z. Good. And then this is defined here as the limit. Both m and n go out to infinity. We want to sum from I out to m, sum from j1 out to n. And we want to evaluate the function at points p sub ij, and then multiply that by small change in the area. Good. So that should be a familiar type of quantity where the only thing that's being changed is instead of a single integral, we end up with double integrals, hence we come up with 2 summations. And then the upper bounds, we want both of those to go out to infinity. Okay. And then as before, we get that the surface area can be related back to the area in the plane if we scale the area in the plane by this quantity here. And so we have something very familiar as before. 618 is updated as 619, which now allows us to take as integrand any scalar valued function. This notation here, let's make sense of that a little bit. That if we're looking at the function, we want to evaluate the function at a point on the surface. A point on the surface is given by x, y's, and z's. But our trick is to go from that curved surface and turn it into a strict 2-dimensional domain in the plane. And that means that we're going to take a u and a v and pass it through a position vector in order to produce that point in 3 dimensions. Thus, our integrand is f at a point, but how do we get that point? We need to look at the position vector. So this is P, capital P. Okay. And here the book is just making a comment on the similarity for a surface integral, and nice typo here. Double integral, that should be a single integral. Surface integral and line integral. That we have a same expression, that we take the flat or Euclidean differential and then scale it by a norm of a derivative. Here we have to have a derivative in 2 directions. Here we just have 1 direction. That's corresponding with the domain of integration. Okay, let's do an example. So in this case, our integrand is this nice quantity here, nice polynomial. And then our domain of integration is this cylinder. And the cylinder is cut off from the xy plane up to the plane where z is 3. And then the cylinder has a radius. The radius is 2. So that's r equals 2, or x squared plus y squared is equal to 4. So hopefully you know how to parameterize this surface. R of x, depending on u's and v's, is done by letting r equal 2, little r. Then we can do cosine u to sine u. And then that will produce any circle of radius 2. And then you want that at various heights, and you want the heights to vary from 0 to 3. So that needs to be in another second variable. We've already used u. So next, let's use v for the height. Okay. So let's make sure that the way that I've just written it down is the way that the book did it. And indeed, that is what the book did. So here's the parameterization. That's your starting point if you're trying to compute a surface integral. You want to look at the domain S and find a parameterization. Then having that parameterization, you're going to need to use that to upgrade or translate the surface area differential into a flat differential via this scalar quantity. And that scalar quantity takes a bit of computation. You need to compute each partial, then compute the cross product, and then take that cross product and look at its norm. And then in this case, we're getting a norm of 1. So straight 1 to 1. All right, very good. And then I invite you to go and verify the rest of the computation. Okay, one more example. This one's a little bit more involved. Looks like we have a dome, and that a part of the dome, they're calling that S, is a portion of the sphere, but they're also including this flat portion there. So let's take a look. So the sphere is of radius 2. But then we also want to include the plane z equals 1. So there are 2 pieces. So they're going to say that S, the surface, has the portion on the sphere, S1, and then marry that union with portion in the plane, z equals 1. So rho equals 2 and z equals 1. Let me put a highlighter here. S1, rho equals 2, and S2, z equals 1. Okay. So then let's take a look at each piece. If we do S1, S1 is the portion of the sphere. Excuse me, I have that wrong. S1 they're taking to be the plane. I have that wrong. Let me go back and change this. So S1, they want that to be the plane, S1. Our integrand is f given by z squared. That's the integrand. So on S1, f is going to be z squared, but z is 1, so f will be 1 everywhere. So that makes it easy. So let's see. Right. So S1 is z equals 1, but it's not the entire plane. It's only a portion of that. It is the portion that's cut out by the sphere. So just that little disk there. So when we look at z equals 1 and rho equals 2, we can grab rho equals 2 and rewrite that as x squared plus y squared plus z squared is equal to rho squared, 4. And then plug in z equals 1 to get x squared plus y squared plus 1 equals 3 equals 4. And then subtract the 1 from the other side to get x squared plus y squared is equal to 3. And then that tells us this circle, the equation of that circle. So then we want everything in between. And then everything in between or inside of that circle is, again, given by, let's write it out. So S1 then has position vector R sub, let's call that R1, vec of uv. Need x, y, and z. Z is easy. Z is just going to be 1. So S1 again is a nice circle, and we want everything inside that circle. So we need a bunch of concentric circles. Here's one, here's another, and so forth. And then the only thing that we need to do is say that each of these circles will have a radius of u, and then move around a radius of u, cosine v, let v be theta, and then u sine v. Alrighty. So what are we doing in this example? Well, we have a surface which is given in 2 parts. The first part is occurring in this plane. And what we did was we looked at the 2 equations. Z equals 1, rho equals 2. That gave us the equation x squared plus y squared equals 3. Then we know that we want everything inside of that circle. So we've come up with the parameterization for S1. And that means that we're able to compute the surface integral over S1 of our scalar valued function f integrated with changes in the surface area. But this surface area is flat. And we are going to find that the size of this normal vector is just u. So in the next slide, we'll see that this is going to yield a double integral over a domain. So we want to go from, let's do u's going from 0 to rad 3, 0 to rad 3, and then v's from 0 to 2 pi. We know that f is constant 1, and the size of this normal vector is just u. So we'll pick up a u as our integrand. And then I chose to integrate first with respect to v, dv, and then with respect to u, du. There's nothing in v here, so we'll just pick that up. That gives us a 2 pi. U integrates to u squared over 2. Evaluating u at bounds, u squared at rad 3 is going to give us 3 over 2. And that's just 3 pi. And so that's what they find. Very good. Next, considering the dome, S2. So S2 is on the sphere, rho equals 2. But rho equals 2 is the entire sphere, and we only want a portion of that sphere. They're recalling what a parameterization of the entire sphere is. And when we look at, let's draw this picture here. When we look at the sphere, so let this be in the xy plane. This is the z direction. Represent the sphere with a circle. That circle will be of radius 2. And we know we want to intersect with the plane z equals 1. And then the picture that they have over here is looking at, is introducing this diagonal, and we know that that is of length 2, that the height of the right triangle we're looking at would be 1. And from before, we know that when we take a cross section with the sphere, we get a circle of radius rad 3, so that's rad 3. And what that is doing is it's saying that if we take phi, here's phi is 0, here phi is pi over 2, here's phi is pi, that we want to stop at this angle here. So from phi equals 0 out to phi equal this angle, we will be pointing to a point on S2. And since these are nice numbers, we can see that we're going to want phi to vary from 0 to pi over 3. Excellent.